in this module 5, we are starting the control volume analysis. Okay, and the first thing that I'm going to do in this is I'm going to look at the conservation of mass. Okay, and after that I'm going to do conservation of momentum, module 6, and conservation of energy, module 7. This whole module is based on the Reynolds transport theorem. Okay, and I'm gonna rewrite this from previous segment from module number 4, but this is what it is. This is the dB dt will be equal to del t of triple integral over the control volume rho b d volume plus over the control surface rho b v dotted with n dA. So this was my Reynolds transport theorem from the previous segment. So now what I'm going to do is I'm going to actually go ahead and read the title of the module, mass. Some people refer to the conservation of mass as continuity equation. That's quite alright. I would like you to be aware of that. But at the end, I'm going to do this capital B is equal to mass. Okay, let's go ahead and write this. Capital B is equal to mass. What do you think I'm going to do for the conservation of momentum? I'm going to say capital B is momentum. What do you think I'm going to say for conservation of energy? I'm going to say capital B is energy. If you remember, this capital B was the extensive property, right? And there's a corresponding intensive property that is defined by B divided by mass. In this particular case, by chance, it seems that, hey, this is mass over mass. So what do you think this is? Well, 1, right? Mass over mass is 1, or unity. Okay, so then I'm going to insert here 1. I'm going to insert here 1. So basically, I'm going to drop those 2 out. And I'm going to go ahead and insert in here mass. So then you're going to get dm dt will be equal to del t of triple integral control volume rho times d volume plus over the control surface rho v dotted with n dA. Now I have to rethink one last step before I finalize this equation and box it up and call it a day. Is remember that this was for Lagrangian, and this is the material derivative, right? Capital D. And also, if you think about it, this will be for the system or control mass, right? And right hand side was for the Eulerian reference frame, and this was for control volume. As you can clearly see, control volume is here, and this is the boundary of the control volume. So now let's reassess the left hand side over here. This is a control mass. If you look at the previous segment from module 4, when I tried Reynolds transport theorem, what I did was I was moving with the flow, if you remember. I was not adding any mass, or I was not leaving any mass from my system. It was a constant number. So in that particular case, for a control mass, the definition was no mass leaves or enters. Then what this term is going to be is, it's not going to change over time. My mass is constant, okay? So this term will be 0, okay? So let's write it over here. dm dt 0 as m is constant for the system or control mass. I mean, this is 0 on the left hand side, so I'm going to write the 0 on the right hand side, because I want to think about it, you know, summation. You don't say 0 is equal to summation of the forces, right? You say summation of the forces is equal to 0. So from the same convenience, I'm going to write it this way. Del t, and we have this control volume, rho d volume, plus over the control surface, rho v dotted with n dA will be equal to 0. Now I can go ahead and celebrate this. We have special names, so this very first term that I'm seeing over here is basically, if you think about it, let's actually indicate here. What is rho times v? That's mass. This is how the mass changes over time for my control volume. Well, it's fairly self-explanatory, right? So it's time, rate of change, time rate of change of mass for the CV. Okay, and this second term, if you remember, I had it in the B dot. I call that flux, right? So this is the mass flux entering or leaving the controlled volume. Is you see this is a volume, and I have a line across the V symbol, and this is a velocity. Velocity is far more common than volume, you will find out. Okay, so I would like you to be careful about differentiating these two. And also, if I continue this approach, what I can say is, do you remember that what was, let's actually write this because I don't think we all remember. So V dot N from the previous segment was plus V for exit minus V for inlet and 0 otherwise. Okay, you may want to revisit the previous segment to double check you know this clearly. So basically this is rho times, let's say this is an exit, rho VA, or rho minus VA, or rho 0. Well, that's gone, right? So basically it is either plus rho VA or minus rho VA. Oh yeah, I got the point that, hey, there's a double integral in here, but hey, that's just a mathematical operator at the end of the day. It's not going to change my units. It's not going to change the way that things behave. Okay? So the integral, actually, if you remember from the definition, is simply a summation sign. So I just take small strips and I add them up under the curve that I have. So the last term that I have over there, rho V dotted with N dA, can be written as m dot exit minus m dot inlet. And m dot, this is a very common terminology that I use. M dot is called the mass flow rate. Okay, so I use this a lot. So this is, you know, one thing when students see this is they start to celebrate because they think, okay, good, I get rid of the integral, I just see what the m dot is and I subtract from one and another. Well, to calculate the m dot, you need to do the integral. So basically my m dot exit will be double integral over the exits rho v dA. Okay, so this is the net mass flux exiting, and I will have a similar for the inlet, obviously. And let's not forget the negative sign. So that's going to be over the inlet, and then I will get rho v dA.